because I talk at Bankiet, I probably skip most of it. I just mentioned that there is some mystic connection probably established in Arava Desert. After we finished the review, we went trekking in the desert, and after that, I had one daughter born, and Christoph two, and Massimo three, and we had no daughters before, so there is definitely some. Anyway, this is our last meeting in Krakow, and Christoph looks sad because we were failing over and over and over again to do what we, even to understand how to do what we tried in the last years and in different ways. And this is to do something for turbulence, which was so successfully done for critical phenomena. And so this talk will be and yet another attempt, which to a large extent inspired by Christoph. And because there is a mixed community here, I want to say from the very beginning, turbulence is generally not a field theory, even though there are many particular things, not many, unfortunately, much less than we would like to see. And one fundamental reason is generally what is considered in field theory is probability distribution, which could be written for a single time quantities, and it has a nice form. It might be complicated, but it's exponential. Let's say it's Gibbs state, so it has a Hamiltonian is non-quadratic, but generally it has a nice form and it's local in some sense, and this type of system is considered. There is no reason, despite that many people try, to accept very special cases like passive scalar in Kraikman model. There is no reason that the turbulence statistics will be like this. And on the other hand, in field theory, we have this success of renormalization group, which is not necessarily restricted to single time quantity. Of course, it could be dynamical. And this is what we were trying to understand, how one can actually build that type of description. And in particular, can we find something to reproduce the spectacular success of epsilon expansion so that we can really start from something. And of course, we did it for passive scalar, but this is for magnetic field massive. But it was a very particular thing, and also it's also this feeling I had, and Christoph also had, that something was missing. And I think that maybe it's what I'll try to do now. At least from my perspective, I start to see one element which was missing, and those are my co-authors, and that's Fibonacci. That's not my co-authors. That's a great Italian, and this is a series of work, and one is still only on the archive. It's about a very simple model. But before talking about the model, I would talk about the idea which essentially inspired us, and this is a very old idea by Vilcik and Cardi and Kitaev and many other people. And it's about how one can distinguish system at criticality from a system which is not at criticality. And in particularly what in this very old, what we had from referee report saying that this guy used some absolutely old obsolete ideas and tried to apply it in the new world. It's really an old paper, and where these people say that if you really look at an entanglement entropy, or you look at the entropy and see what is a kind of a subleading term, because the entropy itself is extensive. It's a linear in the number of degrees of freedom. But if you look at the entanglement entropy of any piece, that you would see that it's logarithmic. And the factor in the logarithm, in a sense, is a sign that you are dealing with a multi-mode fluctuation, that you do with a fluctuation of different scales, that there is some kind of a that the system, and this would be a sign that the system is indeed at criticality. It's totally unpractical to compute entropy for any reasonably large system because you need this multidimensional space and you need to fill it with data, and of course it's factorial. And yet, in some Kitaev and co-author succeeded spectacularly in some particular class where, in a sense, you can do some things analytically and then you can do some things numerically. It's not a straightforward computation of multidimensional probability distribution and taking average logarithm. But what indeed they found out, as seen in this graph, is that you see that there's, as a function of a number of modes, at some cases its entropy goes into a constant and it's such entanglement saturates, but in the other case, when you tune the parameter, it continues growing logarithmically. And that was essentially a sign that you indeed can see that. Of course, Cardi did this also. There are many papers now in this direction. So that's more or less what was the inspiration for us to find something where we can establish a bridge between critical phenomena and turbulence, not on a trivial ground, like say, okay, you see power law correlation function here, you see power law correlation function, something on a little bit deeper level, and all the more that the fact that if you really establish logarithmic dependence, then the factor in front is something which is allow you to classify the class to which you belong. This is the central charge of your respective field theory, which at least describes this slice of statistics. Now a model. A model is, again, is a very old and Itamar in particular, we essentially work on the model that Itamar at some point introduced with Lvov and others, but it goes back to Arnold. And Arnold noticed, which I think probably most of you know, I just briefly repeat it, that Euler equation for a solid body and Euler equation for fluid, which is essentially the same equation, mathematically speaking, just one is ordinary differential equation, the system, and another is partial differential equation, it's equation of geodesics of some metrics, and this the inertia tensor, if you wish, for a solid body could be different, but generally it's just a family of models which equation is has a quadratic part, so it's ddt of some vector, maybe infinite dimensional, equal to quadratic combination of this vector, but despite the fact that it's nonlinear, it has a quadratic invariant, and it's important that it has a quadratic invariant. And then Obukhov kind of generalized it, and Arnold used it. He never used it for turbulence. Arnold used it for stability. It helped him to establish stability of different hydrodynamic flows. But Obukhov explicitly suggested to use it for turbulence because he says that this is essentially a set of interacting modes, and you can really go and increase the number of modes, and in a controllable way, you can see how you actually get from ordinary differential equation to something which resembles real fluid. But what we consider is, and again, probably the first example was in this work of Prakash and Lvov, is we consider the system also to be Hamiltonian. And in a sense, what we noticed some time ago is that if you take a usual wave system or oscillator set Hamiltonian, which has quadratic part and cubic part, but you assume that on the cubic part, your interaction is only between resonant modes, namely that V, this factor, which is it's a Hamiltonian, is non-zero only if omegas are in resonance, then you can eliminate this term just by gauge transformation. In a sense, you hedge gauge invariance of the system with respect to it. So again, you are back to the same type of models in which you have a quadratic nonlinearity. Moreover, because this resonance, you can show that not only Hamiltonian is conserved, but these two parts of the Hamiltonian conserve separately. So you do have quadratic invariant in this case, and it's essentially this type of system belongs to this class, which was kind of an occasional discovery because I'm interested naturally in this wave turbulence for long time, and this is a separate program going on to totally destroy weak turbulence. So now what we do, we'll work with this system and we do turbulence with it. Namely, we apply a forcing, which would be just a Gaussian in-time forcing at a given mode, which is pi would be the power of our pumping. It will be concentrated in some I, and there will be just a dissipation, and then you can convince yourself that your k is just a cubic part of the Hamiltonian, that it's on average is 0, and of course you can have a equilibrium with this system. If you have equilibrium, if you have some kind of a fluctuation dissipation theorem, so that for every mode your forcing and your dissipation are connected, and in this case you will have equipartition. We consider in a very kind of specific case where this interaction will be shell model type, namely only neighboring modes interact. There are different families over here, and we already checked 3 different families. More or less phenomena are the same in all these families. But the point is that if you are in equilibrium, namely, you have such a relation. This is something which determines the quadratic part of your Hamiltonian, in this particular case, omegas. It's called here F's for some wrong reason. Your probability is exactly Gaussian. Namely, that you would expect that your probability is exponent of linear combination of conservation law. You have quadratic conservation law and cubic conservation law, but cubic term makes your probability not normalizable, so you can show that the factor in front of a cubic term is 0. So at thermal equilibrium, it is exactly Gaussian statistics, even though the system is strongly interacting. There is no weakness of interaction in this case. Of course, you can show it pretty easily just by writing Fokker-Planck with in contact with the thermostat, but it's also established, and I cannot prove it for my canonical case, namely if I take a closed system, then, for example, 3 modes are integrable, 4 modes they have kind of partial integrable structure inside. As the number of modes increases, it's getting into really chaotic regime, and its probability distribution goes into this Gaussian. I cannot prove it. It's a very nice problem for mathematicians, I guess, to show that in this case, when the number of modes goes to infinity, and even in microcanonical, the interaction provides for Lyapunov exponent and chaotization, but empirically we find that this is the case. So at least in the limit of large number of modes, both this system in contact with the thermostat and this system in a microcanonical case is in equilibrium with exactly Gaussian statistics. And that's very beautiful, which means that the moment that we start to deviate it from equilibrium, we also deviate it from Gaussianity, and in this way we could kind of see how on our way to turbulence, what we change statistically. And of course, then the case is trying to realize this Wilson type expansion that we were looking for Gaussian distribution. And so the turbulence is in some sense is close to this Gaussian distribution. And then we can try to do perturbatively analytically something about it. And let me describe how we actually found such case. So moment you start doing turbulence means that in your pumping and your dumping are far away. So you pump some modes and you dissipate some other modes. And in between these modes, you have some kind of a transparency window. And so you're looking to describe statistic in this window. And what you can say is that because you have a quadratic invariant and you pump it here and you dump it there, it must be a flux, and this flux must be constant. So you're looking for some kind of 4/5 law which describes this flux, and it immediately tells you that you know exactly what is the triple moment in the system. The triple moment for modes which are far away from pumping and far away from dumping is given by a particular. And so what we now consider, this is a particular case, and maybe later I'll show you. It's a interaction of 3 consecutive modes, namely that I would only assume that mod I and plus mod I plus 1 give me mod I plus 2. That means that my frequencies, which are in resonance, must be Fibonacci numbers, and that's why we call it Fibonacci turbulence. And Fibonacci are called F. So this F's are Fibonacci numbers, and so this is my equation, and I can write a flux, and the flux is of course expressed in terms of the third moment, and I can find the steady solution, and I can use some kind of exact Cassini identities for Fibonacci to show that indeed it is a constant flux, and it turns the equation on the second moment into 0. Excellent. Now, it was an issue in shell models, and Itamar and Luca and Erika, there were many papers which were trying to sort out in which direction actually your cascade goes, because in principle, in such kind of models, you can have a cascade going in both direction. Usually in shell models of that type, they have two quadratic invariants, and there could be different issues with different. In our case, we have only one quadratic invariant. But I just probably skip these details. They are less relevant to the main subject. You can show, because in this system, it's a chain of interacting modes. There is no space. There is just only mode number. So in a sense, from a usual complexity of turbulence, which is spatial temporal, what is here left is only time. So there's modes interacting with each other, and some modes are faster and some modes are slower. So this is the only thing which distinguishes one mode from another, but in a very strong way, because the frequency is a Fibonacci, and Fibonacci grows exponentially with a number of modes. So what we were able to prove would be probably a strong statement, and that cascade goes from slow modes to fast modes in this case. And again, by and again, when I mean slow and fast, I don't mean frequency. I mean the typical interaction time. So when you write the equation, you'll see, for example, over here that in this distribution, this is an equation just for amplitudes. I mean, this equation has an invariant subset of only imaginary amplitudes. And then you can substitute the scaling that you obtain out of flux constancy, namely you kind of Kolmogorov-like scaling, and you can establish how typical time depends on the mode number, and of course it depends on the scaling of your interaction, of your interaction coefficient Vi. So you assume that it has some scaling, namely defined by alpha. Alpha is how fast interaction strength increases or decays with the mode number, and then you can find this turbulent solution in terms of this alpha, and then you can show that cascade always goes from slow modes to fast modes, which I guess physically is probably meaningful, because if you drive fast modes, then they essentially establish equilibrium for the rest of the system, because they act like a thermal noise. Now, when you look at this turbulent solution, then you may ask, by changing parameter alpha, when it coincides exactly with the thermal equilibrium, with equipartition. And then you find out that it requires alpha to be 1/2. And so you say, okay, let's take this system with alpha 1/2 and start driving it. Now, it cannot be in equilibrium, because you drive it in only in the mode in which you do not dissipate, and you dissipate mode somewhere else. But in this case, alpha 1/2 again, naively speaking, in terms of scaling, all your modes interact with the same speed. So the typical interaction time, if you substitute the scaling, would be independent on the mode number. So essentially you say, my cascade does not know which way to go. And it's true, it goes the way you want. So in this case, you can have both direction of a cascade. So it's kind of a double cascade picture, but for in a very special case, it depends where you put your damping. So you really can have is in between. So here, what is shown that when alpha is 0, you have inverse cascade. So here you see pumping put at the mode, in this case, you see the pumping is put over here, and your cascade goes here, and your equipartition to the right. When alpha is unity, it's other way around. You put pumping here, you see that the cascade goes in this direction, and you also see a constant flux as you derive, and you also see that this a third cumulant, dimensionless, what we would call skewness. The skewness, which is dimensionless ratio of my third moment to the second moment, the power 3/2, it kind of goes down when your alpha approaches 1/4. And it seems that indeed, when you go towards this case, then your turbulence approaches this equilibrium, and equilibrium has a Gaussian statistics. And again, you can see that when you take alpha exactly 1/2, namely V is the square root of Fibonacci number, you put your pump in here, you have cascade in both directions, you put your pump in here, you have cascade in both directions. The fluxes are shared in inverse ratio of lengths, so it is indeed a very beautiful case where you have a scaling of turbulence exactly coinciding with the scaling of equilibrium. Your distribution cannot be Gaussian and cannot be equilibrium because it must carry the flux. But somehow you expect this flux to be small and your statistics to be in some sense close to Gaussian. And at that point we were ecstatic because we thought, okay, here is the Wilson case. We do have something which could be probably treated perturbatively. And it is here where the main surprise expected us, which means it's not all lost, but it's much more interesting and complicated than we expected, and that Wilson had it in his work. So first, when we really look at the probability distribution of a single mode, which is generally, if you're far away from equilibrium with alpha not equal 1/2, it's a multi-scaling, it's a normal scaling, it's getting more and more non-Gaussian as you go along cascade. Here it's not. You can just see different modes in statistics is practically Gaussian, and you also can look at different moments, and you see that as you go away from pumping, they all approach exactly Gaussian values, which is the meaning is that if you look at a single mode, just it practically has the same statistics as equilibrium, and the statistics is Gaussian. Of course, it has third moment, which means that it is not exactly Gaussian, but what we established that it's small, and then you ask, okay, it's Gaussian, but what is the dependence of the occupation number of the mode number? Because it could not be exact equipartition. If you would have exact equipartition, you would have no flux. And you must have flux because you pump here and you dissipate over there. It's no surprise, you establish that it's logarithmically distorted. So it has a power law which is exactly like in equilibrium times a logarithmic factor which distorts it in a way that then you have a flux flowing from pumping to dumping. Okay, we can do what I always dream to do, take equation and try analytically to derive correlation function. Well, we did it once with passive scalar and other people did this. So this seemed to be the case where one can try to do it in a system with no weakness of interaction. So the small parameter here is that you're really working for some specific class of system in which the scaling of interaction is such that you are close to equipartition. So you introduce the general type of cumulants. They all must be gauge invariant in a sense that only such cumulants are different from zero, from which respective Fibonacci's are sum to zero. So it's kind of this gauge invariance imposes this class. And then you just write Hopf equation. And that's what we started to do. So you write ddt of the second moment. It's expressed through the third moment. So you require that your third moment is constant. That we already passed. This is 4/5 law. And then you write equation for the third moment, and you get right-hand side, which is essentially different combinations of fourth order moments. Then you make an assumption which is at this point, it is an assumption, that your statistics is close to Gaussian, and then moreover, that your pair correlation function, which is determines this Gaussian statistics, is close to equipartition. And then you substitute it, you happily see, no surprise, that the right-hand side turned exactly to 0. If it's Gaussian, then you look for a small correction to it, and you get equation for the quantity which here have two indices is the third moment, so the quantities which have three indices, these are actually four fourth order cumulants, and so you get some equation for the fourth order cumulants, and you see that it is essentially expansion in the parameter epsilon, and epsilon is to alpha minus 1, and then you say, okay, now let's go to this logarithmic case, d equal to 4 case, if you wish, if you use analogy from critical phenomena, and here you get a relation, so you express your fourth cumulant through the product of second cumulants, and you see that here this is has this form that the fourth cumulant indeed is suppressed with respect to the A4 is just n squared, so this is A2 squared essentially. This is a Gaussian part, and this is a cumulant, and you see that it's suppressed, and it's surprisingly the suppression factor is a number of mode, its distance from the dissipation scale, not from pumping scale, but from dissipation scale. It's a peculiar case, and I won't even don't want to speculate here, but this is just a result of computation. So essentially, it tells you that you have pumping, and then when you come to damping regions, then you have a dissipation which is of order of your interaction, and in this region of damping, your statistic is substantially non-Gaussian. It's always non-Gaussian at the dissipation scale. It's could be very close to Gaussian in the pumping scale, because your pumping is essentially white Gaussian noise. So if you make it really longer and longer and longer, then both on the pumping scale and in a wide interval, you will have statistics which is close to Gaussian. So essentially, here that you really deviate from Gaussianity as you go towards damping, as you go along the cascade, but in a very, very weak way. Because again, this is a linear, well, 1 over mode number, but my frequency Fibonacci is exponential in mode number. So this is essentially a logarithm of frequency. Okay, and okay, so that was the fourth cumulant, and then you go forward, and then you write the respective equations for higher cumulants, and you establish, to much surprise, at least it was surprised for me, that they aren't small with respect to each other. So the higher you go, so when you go from 4 modes to 5 modes, to 6 modes, to 7 modes, all these cumulants have the same scaling. So they aren't suppressed more than your already third cumulant was suppressed with respect to the second in the power 3/2. So essentially, this is what is expressed in this last line. So if you define a dimensionless cumulant, which is your cumulants divided by just Gaussian, just take it modulus squared, and it's something which is non-zero already on Gaussian distribution, they all are suppressed by the same factor. So I think that maybe even apart from everything else, this is already something which I think is new, because kind of normally we thought about kind of deviation from Gaussianity in terms of a structure function, which in this case would be just amplitude of mode I in some high power, and it would have an anomalous scaling. Here it has a normal scale. But when we work with wave turbulence, we usually thought about energy, which was kind of second moment, close to second moment if we had weak nonlinearity, and flux, which was a third moment. and I never thought about what is behind it. What are the multimode correlations? And essentially, what this direct computation teaches us is that the moment that you have a flux, and it's a flux which is third moment, you would have fourth moment and fifth moment and sixth moment, as they all of the same order, at least naively counting powers, even though it's a system with only three-mode interaction. So there's no direct interaction between distant modes. It's a shell model, only neighboring modes interact. So I think that already this was is a lesson, and probably we can get more out of it. But unfortunately, when I go to higher moments, the number of cumulants increases factorially, and I cannot write closed equations so that I can get factors. So of course they all have the same scaling, but maybe the factors decrease so fast that you can really disregard this cumulants, not by a power of whatever mode number, but just by some kind of factorial factor which tells that the dimensionless cumulants will be small. Okay, and because there are many of them, and again, if you look here, because what matters is the dimensionless number, but this denominator has a large factorial factor. It's a Gaussian average, so it has this n double factorial, and so maybe it will suppress it, and then you can forget and live happily ever after, and do your perturbation theory only with the second moment and the third moment, because it's difficult to do Wilson sink with infinite number of charges when you have. So here we did numerics, and again, it's a very happy case, this alpha equal 1/2, that the interaction time is independent on the mode number. The main difficulty, as anyone would confirm, I guess Itamar can confirm, that your interaction time decreases exponentially as you go along the cascade. So it's getting very, very short. So you need a very short time step. The longer the chain that you want to consider, you need a shorter time step. And it's getting totally unpractical when you are, people did like 20 modes, like 40 modes. And here, your time increases not exponentially, it decreases. Your time decreases by a logarithm of this exponential, which is a power law, and we can afford 200 modes, which people never had in shell models. So we really pass, for this you need to pass to right variables. You don't have it kind of directly, you need to pass to renormalized variables, and here are the results. How I'm doing this time, Massimo, taking into account that 10 minutes, okay, good. So this is a heroic computation by Yotam Kadish and Natalia Vladimirova, and so here you see the cumulants of different orders, and it's kind of it's a mess. I mean, I really think that this mathematician can probably, there is some very beautiful algebraic structure in all these things, which is probably beyond my abilities. But I'm interested in the quantity, which maybe I'll show over here, and then I will return to it. I'm interested, again, coming back to my initial thing, I'm interested in the entropy. Or, of course, again, entropy is linearly growing with a number of modes, so I'm interested in the relative entropy, in the Kullback-Leibler divergence, as they say, between my true distribution that I have, which is close to Gaussian, but it's not Gaussian. It's close to Gaussian for every mode, but not for all of them, and the Gaussian distribution. So I'm asking how different is my probability distribution from a Gaussian distribution. For this, I need to compute Kullback-Leibler divergence, which is P log P over Q, where P is my distribution and Q is Gaussian distribution. And if you assume that you have a set of cumulants and they're small, you can prove that this is just this relative entropy is just a sum of squared cumulants. That means that what I will be interested in, going order by order to different cumulants is that I'll be interested in the squares of these cumulants, because when you go to higher cumulants, some of them are getting smaller and smaller, but their number getting larger and larger. And so I'm interested in how actually it comes out. First, we analytically computed the dependence on the mode number. You remember this 1 over I minus d, and this is a numerical confirmation that indeed, if you properly rescale it by I minus d, then you would see that they follow scaling, and this is different orders, how they follow scaling. And also, if you look at the numbers, you see that they are comparable, at least. And then you see that the scaling is correct. And unfortunately, there is some really beautiful, some of them are very small, some of them are comparable, and there is some algebraic structure behind it, which I don't understand at the moment. Just to make sure that this is not a peculiar property of this Fibonacci model, we consider even simpler case, which is, this is, by the way, is kind of interesting for optics. For laser people, we can consider a second harmonic generation. So this Hamiltonian, which is here at the bottom, is of a very peculiar kind. So this you have mode I, two mode I's given mode A plus 1. So this is kind of a cascade of second harmonic generation. In this case, this omega must be 2 in the power I, and then you would have this resonant case. So just for to make sure that this is a more or less universal phenomenon for this class of model, we did the same, and this is a master student, Yotam Kadish, who did it, and we found out that this is analytic computation are even simpler in this case. Again, as you go to the beyond fifth order, one particular case of sixth order, I can compute the number, but generally you cannot compute the factor, only the scaling. And so you do numerics, and this is also numerics with such resolution. So this is a table. So H3 is Fibonacci model, H2 is a cascade of, and you have again a direct and inverse cascade because we're in this symmetric case. And so you see that even though, and we cannot go beyond seventh order, unfortunately. So it is not a proof in any way that it's true for arbitrary order. It's at this point, what we know for arbitrary order is the scaling, but not the factors. But again, coming back to this question whether we are at criticality, whether our relative entropy would be logarithmic, I need to look at this double sum. In this double sum, I sum over a mode number, and I sum over order of cumulant, over m. So because all this d is 1 over I squared, then if I would have only single sum over modes, it would be convergent. So I really need that this is I minus 2, and this is summed over both this and this. So this thing has a limit which is finite when my m order, and when you look here, that you see that it's non-decaying. It's not a proof that it's actually getting finite, and already seventh order there are 70 different cumulants, so it's really numerically it's a heroic effort to sort them out and not to miss a single one of them, and then accurately compute them. Takes sum of squared, but at least up to seventh order it seems that this is non-decaying. It kind of fluctuates from order to order, and even orders are different from odd orders, but it's non-decaying, so there is a reason to believe that it has a logarithmic dependence. So let me kind of wrap it up. This class of models, which I neglected for long, I thought that they're indeed artificial. There is no space here. But again, like in the passive scalar, what Krajkman, the genius of Krajkman, realized that the temporal structure of velocity is irrelevant. What matters for anomalous scaling is a spatial structure, non-smoothness of velocity. In this case, it's kind of an opposite limit, it's no space at all, it's only time. That we really go from slow modes to faster modes, and that what kind of establish this non-Gaussianity expressed in terms of multimode correlation. But this is really something which is probably the main message is that it's multimode. So multimode correlations are as interesting and as important, and in particularly, this is on a level of assumption at this point. If indeed it is something which is non-decaying with a mode number, then it is like a critical case. So we'll have entropy logarithmic, and if we compute factor in front, that maybe that would be something which would tell us what actually it is, this class of models or that class of models. So as you see, this is very much work in progress, but at least these two lessons I think we learned here, and I'm now very much excited about multimode correlation, which I kind of never studied before. Thank you for your attention.
You had alpha equal 1 and alpha equal 0. The fact that there were bumps, was it finite size effects?
There was just
it's just finite size effect
on a pumping, but I also
no, but it was a standing. No, it's not the little bump. You know, there was kind of a non-scaling behavior.
In one cascade. The point is that when you have, you see, we cannot have large equipartition on one side and large cascade on the other. You need to sacrifice. So when your number of modes in equipartition is small, it's actually distorted. So you really see that it's not exact equipartition. And again, direct cascade is different here from inverse. So this is a lot of different subtleties. So I guess that you probably meant this. So
the next one.
The next slide.
The next slide. Yeah, that one.
Yeah. Well, so this is something very non-trivial going on when you pass. I mean, because this is a skewness, right?
Yeah.
So you see that indeed it has some kind of a constancy, but it has a non-monotonic dependence. So there's just to sort it out at pumping and at damping, it's a non-trivial task. Actually, when I'm trying to do a randomization group here, I initially try to do it like this. Like I start from pumping and then I average mode over mode. It's very non-trivial. It's really because it's, you know, it's just kind of, but so it's not understood clearly what's going on.
Just a curiosity on the previous, okay, this one. Why? When you have alpha equals 0, you pump on large modes, and then when you put alpha equal 1, you pump on slow modes.
Because I know that my cascade would go from slow to fast, which means that I know that that in this case I know that my cascade would be inverse on the left. So I put my pumping closer to the right, but I can put it over here. Then I would have equipartition.
Okay.
So you see, the modes which are slower would be in equipartition. The modes which are faster would be in a cascade.
Okay.
So you put it.
Okay. So you know the results before.
Yeah.
Any other question? If not, thanks, Grisha, again.